In this chapter, we build on what we learned in the previous chapter. We add a few more details and components as we begin to amplify signals. We have seen this circuit before, but now we've added capacitors, although we don't have the value for the capacitors yet. Notice that we put an input signal at the base and we take the signal out at the collector, and we're going to call the output V out. As always, let's begin at the base, and we can say that voltage on the base is 10 volts times 2.2 kiloohms divided by 10 kiloohms plus 2.2 kiloohms, and that equals 1.8 volts. Then we can say voltage on the emitter is 1.8 volts minus 0.7 volts, which equals 1.1 volt. And then we can say that current through the emitter is approximately equal to current in the collector, which is equal to 1.1 volt divided by 1 kiloohm, and that equals 1.1 milliamp. Now we introduce a very important formula, and that's the AC resistance of the base and the emitter junction. And it's given to us when we say that R prime BE is equal to 25 millivolts divided by collector current. In this case, it's 25 millivolts divided by 1.1 milliamp. That equals 22.7 ohms. An equally important concept is the AC resistance of the collector, and this is given to us by R prime C, which equals RC in parallel with RL. In other words, the collector resistor in parallel with the load, and that equals 3.6 kiloohms in parallel with 10 kiloohms. R prime C then is equal to 3.6 kiloohms times 10 kiloohms divided by 3.6 kiloohms plus 10 kiloohms, and that equals 2.6 kiloohms. Notice that we did the transistor biasing in DC, but now we're introducing AC quantities. We were able to do that because of the capacitors, because the capacitors block DC but pass AC. So we can do two things at once. Let's continue by finding the voltage gain. The voltage gain is R prime C divided by R prime BE, which is 2.6 kilo ohms divided by 22.7 ohms. That equals 114. This has no dimensions, it's simply the gain. We have a voltage input of 2 millivolts, and we're going to amplify this 114 times. So we say that V out, or the output voltage, is equal to the gain times V in, which is 114 times 2 millivolts. And so it equals 228 millivolts. When we do labs, we will see that we will have a high gain, but also that the output will be inverted from the input. Let's take a brief look at the capacitors now. When we're looking for the lowest frequency for good coupling, we mean that we want a certain frequency at which the most of the signal will get through the circuit. That means we're going to input a signal and we want most of the signal to get out to where it says V out. For good coupling, they say capacitive reactance XC should be less than or equal to 0.1 times R. So that equals 0.1 times 10 kiloohms. So capacitive reactance should be less than or equal to 1 kiloohm. Xc equals 1 over 2 pi Fc, but we need to find frequency, so we rearrange the formula so that frequency equals 1 over 2 pi Xc times C, which equals 1 over 2 pi times 1 kilo times 47 microfarad. So the frequency is equal to 3.38 hertz. What we have found is that if we get about 3.38 hertz, more of the signal will be dropped across a 10 kilo ohm resistor, and therefore more of the signal will get past the circuit and will be found at V out. Now, what we want to do is the opposite of coupling, and this is called bypassing. So we look at the circuit though, and we see this a little more complex. So we need to do a little bit of Thevenin. To find the Thevenin resistance, we take the 2.2 kilo ohm resistor in parallel with 10 kilo ohms, and that equals 2.2 kilo ohms times 10 kilo ohm divided by 2.2 kilo ohm plus 10 kilo ohm. That equals 1.8 kilo ohm. Let's redraw the circuit now so that we have 1.8 kilo ohms, and it's working with a capacitor of 220 microfarads. Once again, we say that Xc should be less than or equal to 0.1 times R Thevenin. So in this case, it's 0.1 times 1.8 kilo ohm, and that equals 180 ohms. Once again, let's solve for frequency by saying that the frequency is 1 over 2 pi times 180 ohms times 220 microfarad, and that equals 4 hertz. The difference between the coupling circuit and the bypass circuit is that the capacitor and the resistor are now in opposite places. So now, when we get above 4 hertz, less of the signal will get past the circuit, so less of the signal will appear at V out.